Good afternoon, ladies and gentlemen. That's me again, sir. Today we will go on with our short study of quantum transport scattering, and we will look at something which is really quantum. We'll look at interference of quantum waves. I cannot approach it immediately. Before that, I'd like to give some information about multi-terminal structures. We still, yesterday, we've been talking about nanostructure with only two leads. It's very simple and most important, most practical situation. But one can also arrange nanostructure with more terminals, and we will formulate scattering matrix approach. For this, Landauer formula for multi-terminals will come naturally. I think it's rather technical part, just sorting out what we already know about scattering matrix. Beam splitter will come handy for our discussion. Then, if you, how can I say, usually I skip this point for my master students because it used to be very confusing point for about a decade, also for Landauer himself. I even don't think I have a slide about this, but if you ask me, if you want to be confused, so please ask me at this point. I will tell you about Ron Landauer formula. After that, we will go directly with quantum interference, starting with this very simple concept of double slit experiment, and then we will see how it can be realized in quantum transport. All interference is about phase shifts, so we will look at different ways to organize phase shifts in quantum transport. Around effects, surely it's a heart of quantum transport to some extent. Most interesting manifestation of interference. Right, double barrier, also pretty simple, but very important topic. Good, then we combine these two, but that will be less instructive. And just for a change, I will tell you about some experiments. These experiments are pretty old, it's a classic experiment. And it is my pleasure to talk about this as well. All right. So let us start with a multi-terminal setup. Right, so that's our nanostructure. What it does, it scatters electron waves which come, converting these waves into outgoing waves. The difference is that these waves come from different terminals. So now how many I have? I have actually 3 terminals where current can go. If I look at it, if I forget about the waves and just treat it as an electric circuit, I can apply voltage to these terminals and get current responses in each terminal. Right, they will be determined by scattering matrix, as we will see in a second. What else? If you talk really about a realistic nanostructure, there are also electrodes which are not electrically connected. Yeah, one can think of capacitance, which is connected to nanostructure, an extra gate voltage, When my good friend, famous experimentalist, was asked to define a nanostructure, he gave, I guess, very practical answer. This is something with gates. Right. Why do you need gates? Just to change it to control, to prove that nanostructure works as you expect. I think that I also want to discuss at this stage pretty obvious, but I guess rather important point, or something to amuse first year students. Let me put it in scale. This is nanostructure. So the first lead, second lead, third lead, they become bigger, 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 bigger. So that is a chip, 1 inch chip. And there are some wires, and it is all in dilution reach of about that size. It's real size. How do we know anything about this nanostructure? I mean, if you just look at it with our eyes, we don't see anything.
So obviously we need a microscope.
Well, next time you come to the lab, they give you a task to put this electron microscope into the fridge. I see how would you manage.
Transport experience.
Yes? Let me formulate it this way. Which fundamental law gives us possibility to see such? This is current conservation. We see we can characterize this nanostructure only because we know that all carbon from this coming from this state to go to this state has to pass this little object. And the amount of carbon is determined by a nanostructure. It would not depend on the leads. There is a practical criterion which tells you that leads are not important. You can get this practical criterion.
Not important for what exactly? For
assessing properties of the
conductance.
Yeah, I would rather say resistance, but anyway, the conductance of nanostructure should be much bigger than conductance of the leads. It's ideal condition in practice. In an experiment which I showed you yesterday, the series resistance of the leads has been subtracted from the plot. But okay, there are many ways to remove this effect. Fine, right, because sometimes I forget to mention really very simple things which are very important. It's current conservation which allows us to assess nano-objects in this method. There are optical ways which work a bit differently, but anyway, it is what we are talking about transport. That's how it works in transport. Oh, fine. So what is a transfer problem? We need to express currents in terms of voltages. The simplest problem to solve. Right. Let us define scattering matrix for this chart. It's actually the same scattering matrix. There are incoming waves, outgoing waves. The only point there are different terminals. So it's good to include the terminal into the index of a lead. So indices become double, alpha numbers terminals, and Latin letters number channels coming and outgoing in each terminal. Yes, please, your question.
And the role of the capacitors is then to change the stereo?
Precisely. Yes, I did mention it explicitly. Very good that you asked. Yeah, in this aspect, what capacitors can do is to modify the properties of the scattering matrix, change the numerical values of its elements. So the difference is that it's convenient to use double indices to remember from which terminal you send your electron value. Good. Let's talk about general properties of scattering matrix. It's precisely the same as we mentioned. First of all, there is unitarity. But of course, it's defined for all possible terminals, for all incoming and outgoing waves. That's how I write it. Putting this all indices explicitly, just rewrite condition of unitarity. Once again, Greek indices number the leads, the terminals, and the Latin indices number channels in each terminal. Very good. So, how about time reversal? It's actually the same relation which I used yesterday. Now I rewrite it a little bit differently. I keep in mind that magnetic field changes sign upon time reversal. In order to memorize it, I also have to recall that magnetic field is due to circulating current. So if time is inverted, it will circulate in opposite direction. So the magnetic field will change sign. So that's a relation which defines symmetry with respect to time reversal. It's again about a movie where electron goes from, let's see, from terminal beta in channel M and comes into terminal alpha in channel N. And I could just rewind, I could watch this movie in opposite direction. Good, all right, so let's perhaps do some, first let us understand also a pretty simple question. What do we need to calculate? So in simplest case, currents in all terminals are proportional to voltages. There is a vector of voltages, there is a vector of current, there is a matrix, conductance matrix, which relates these two. Right. General properties of this matrix. First of all, there's current conservation. The sum of all currents going from our structure has to be 0. So whatever happens, the sum over rows of this matrix has to be 0. Additional property. If you raise all voltages in all terminals by the same value, there will be no current response. Why?
Because we never have difference.
We never have different voltages. I used to talk to tell my students, okay, it's another course. Anyway, I used to prove them that in physics we frequently use unphysical quantities. And eventually it's a mere structure of physics that we have to use physical quantities. And the simplest unphysical quantity we encounter is voltage. So given a lead at certain voltage, I could grab this lead and nothing happens to me unless I take another lead. Then I will feel voltage difference. Only voltage difference is present, which means that you can sum up this conductance matrix over second index and get zero. Good. How to reconcile it with what we know about two-terminal structure? Okay, that's how it is. Right. So conductance matrix and in two-terminal setup is actually 2 by 2 matrix. But owing to properties I just described, this 2 by 2 matrix has only one independent element. No, that's not. Right? No questions, no objections? It's so simple, but sometimes you just don't understand how simple it is. So sum of these two is 0. Also, sum of these two is 0. Fine. Let us move to Landauer formula. And let's try to keep it as simple as possible. Let me just talk about probabilities of transmission. In two-terminal setup, we only have one probability. Right? Here, we can have more. So we sum up probabilities to come in any channel from any channel in terminal beta and go to any channel in terminal alpha. All right. Then our formula is expressed in terms of these probabilities. It has very similar structure to what we discussed. So it's current in terminal alpha. We found our central quantity of quantum transport, conductance quantum. We have summation over the leads. Here we have field vectors, right, with indices beta. And what we see in this term that electrons from terminal beta go with some probability to terminal alpha. That's all nature. All right? Do I convince you? Then please explain me the second term.
Outgoing from alpha terminal to another terminal. Yes.
Incoming or outgoing?
Outgoing. Like second term.
Yeah.
So like we have pretty much of how much we have inside the F alpha and probabilities to channels of other terminals.
Yeah, that's right. That we put it like this. current in terminal alpha has contributions for all electrons coming from other terminals. There are also electrons coming in terminal alpha. If all these electrons are reflected, then there will be no contribution to the current. So I need to count how many electrons have been transmitted. They can go to all terminals, so I need to sum up over beta here. Okay? So it's balanced. Any bookkeeper just would kind of, you can explain it to any bookkeeper. Let me put it like this. Fine. Let's run full checks. Current conservation, no current at equilibrium. Do we see that? Okay, first current conservation. We sum up over alpha. Let me put alpha here. That these terms are the same if we change beta to alpha. Yeah?
I'm just for a moment a bit confused. So, this must be a simple question, but if we have the current going into the alpha,
Yeah?
then wouldn't we momentarily expect that the filling factor is
Let's see. Let me repeat again what I was talking about. So it's filling factor in alpha, it's filling factor in all other terminals. Beta is not alpha here. Right. Here it's filling factor in the same terminal. That comes about electrons which come from terminal alpha to nanostructure. Some of them are reflected, some of them are transmitted. If they all reflected, then we have incoming flux and outgoing flux of the same value. But if some of these electrons are transmitted, these fluxes do not match. And this is contribution to the current.
Maybe that's not what you're asking about. You're asking about whether, because of the current, the distribution function of the lead will change.
yes,
Um,
momentarily, yes.
It's not the case because they do not accumulate in the lead; they are evacuated at infinity. Current distribution is uniform.
You're really up to be confused. Okay, then if I will get no requests from all others, I will tell about a Ron-Landauer formula to you personally. Yeah, it's indeed a good question. Sir, I didn't put it explicitly. We assume that, well, leads are massive. All electrons from the lead come from nanostructure. And small guy cannot change the distribution of electrons. They're massive nanostructures. Fine. Current set conservation. With sum of alpha we get 0, current in no equilibrium. Well, we just said all F's to be the same. Equilibrium, and again currents are 0 in any terminal. Good. Foolproof checks are completed. We can use it. Let me rewrite it in terms of conductance. In that case, we assume that scattering matrix does not depend on magnitude. And the conductance matrix can be directly expressed in terms of probabilities. Needless to say, if you apply the same to two-terminal situation, what we get is the trace of transmission matrix squared, the sum over transmission eigenvalues. Right, was fun to check these general relations. That's impossible to check in two-terminal setup, but we have more terminals. One can look at magnetic field dependence of cross conductances. And that should obey on Zager symmetry relations. These symmetry relations just fundamental. They don't care whether it's quantum electrons or whatever ions or just slow people. Right, it's general thermodynamic relation. We prove it from properties of scattering matrix. So conductance matrix at zero magnetic field must be symmetric. If magnetic field is applied, it doesn't have to be. Hall effect, not what to Hall effect, just Hall effect is an example of it. Right, okay, we saw this standard formula. Beam splitter, ultimately simple but necessary element for us. If you look just at, if you want to reduce the number of channels, if you want to think about one-channel conductors, there has to be a tool to split these channels. And this tool is called beam splitter. That's elementary multi-terminal nanostructure. Beam splitter comes from optics. I just choose rather funny but frequently used in optics elements. This is a reflectionless beam splitter. Let's look at it. So if I start insert terminal, here, I look here, there is no reflection. This non-diagonal element is 0. And then incoming wave would be separated equally to 1 and 2. That's amplitudes. If we square it, we just have 1/2, 50% probabilities. It would be cool to have a beam splitter which is reflectionless from all ends. That's not what scattering matrix allows us. It's impossible to make a matrix, scattering matrix, for such a beam splitter, which will satisfy unitarity conditions. One can be happy that there's no reflection from one end. Yeah, as you see, there's 50. Let's see. I need to look at in order to look at reflection, I need to assess diagonal elements, and from all other ends, reflection is how much? How much is reflected if I come in channel 1?
1/4.
1/4, yes. We square probabilities, we sum them up. That's the conductance matrix. It's expressed in terms of probabilities. You see that it satisfies the properties, some of this element should be 0. That's right. So it looks pretty boring by itself, but that gives us ability to split channels in the framework of right. So I should go pretty fast. So we have time for Landauer formula, but I just don't wonder what is the desire. So please raise your hands, people who want to be confused. It is a very thin majority. Okay, good. Then I just have to make transparency. Oh, yes. Landauer formula.
You can use the border, but maybe it's a bit faster.
Let us see. I just wonder if the board is recording.
On the whiteboard, yes, it's called.
All right, then. Let me try to do this. Have something to clean it up.
It is on the whiteboard itself.
Oh, yeah. So, I want to have one general conductor with transparency coefficient T. One channel. So, I have in Kanye wave with a hidden factor F. Let's see, right. And Kanye wave is hidden factor FL. And corresponding outgoing waves. Oh, let us figure out what would be hidden factor of outgoing waves.
Where? If it's in the immediate vicinity of the structure, it's one thing. If it's in the bulk of the leaves, it's the other thing.
In the drawing.
Hmm?
In the drawing. Let us figure out from scatter method. This is scattered and reflected, but there are also a possibility for electrons from the left to counter this. So our field vector would be like this. If I look here, field vector would be all right. let us now make the structure for terminal. I will do it in a very simple way. I will add here a couple of contacts which will work as voltage probes. Left voltage probe and right voltage probe. These voltage probes kind of measure filling factor. Electrons of both directions will come onto this probe. Okay, what will it measure? There's democracy in this probe. So it will be and that voltage probe would measure me?
No. Again, for the drawing, okay, but not in reality.
We are thinking about 4-terminal circuit.
Well, it's already not for terminal because you assume some spatial separation between L and the.
I did not assume any special separation. I didn't say anything about spatial separation. There is no such parameter.
Then it's not correct to say that electrons only from the lead channel to the cell and R, because in this case, from the structure, they also jump down from the structure itself.
That's a local voltage probe. Let's understand the voltage difference. For this we need manage to do it simply. We need to transfer this in effect into actual voltages. So let us set FL to 0, FF to 1 in an energy stream of the base of voltage. Right? And integrate these expressions over the energy in this energy stream. Let us see what we get. Just check if it's voltage. Voltage again, 0. How about left part? 0, 0, 1 over T voltage. That's what the voltage probes would measure in this situation. Right. The current, as we have figured out, is G cubed times voltage times T. But this is for two-terminal circuit. That's now what we call some electricity. For four-terminal circuit, one would determine the conductors as current divided by what?
Voltage between left and right, you want to say?
Yes, that's our four-terminal electric measurement. Let's see, VR minus V left, so let's see what we get. GQ E T divided by let's see, I need to transform it. It's 1/2. 2 is T times voltage, and this is 1/2 minus T. So that will be object if unknown.
V is this.
Yeah. So let me rewrite it. We have alternative Nazarov formula. And the biggest argument between Nazarov himself and academic scientists was in fact skeptical. It was the difference between two-terminal measurement and four-terminal. Landauer itself understood the difference, but he did not manage to convey it to academic colleagues. So they always tell, oh, this guy gives two different formulas, he cannot reconcile it, but that's, if you find it sufficiently confusing. Oh, sorry. All right. That's from another formula. It's an illustration that, first of all, conductance of a structure cannot be defined locally. Right? Two-terminal measurement would work perfectly if you replace this nanostructure by a resistor, by a circuit element. It doesn't work in the world of quantum. I thought I gonna regret it. But anyway, the question?
Can we understand this discrepancy as the fact that in reality electrons quickly equilibrate in the leads? What I would measure with R would in fact be also FR, because I've already lost all the information that I have ever scattered on anything.
The best way to proceed is to understand that there is no discrepancy.
Yeah, that's what I'm saying.
Because I talk about two different circuits with respect to number of terminals.
Yeah, right.
So traditional Landauer formula was for two-terminal circuit,
Yes.
and this is for four-terminal circuit. The confusion is that for usual conductors, the conductance is local quantity, two-terminal measurement and four-terminal measurement deliver precisely the same results. And
the question is then,
which I see is still find confusion.
no, that's exactly, I'm proposing the resolution for this confusion.
But there's no confusion.
I mean, the confusion is, okay, then I can reformulate it. Why two and four terminals give the same result in the normal situation? I can ask this as well. And the answer is because electrons equilibrate between the contacts. And, and here they don't.
It's good that it indicates a problem. Many politicians also do this. The solution which you propose also kind of a bit political. It might work, but it's not complete. We talk a little bit later about this. I promise that in the last lecture I will try to address this problem. Fine. Yes?
Your solution, just
we have derived formulas which are different. And they are different because we consider different circuits. What I solved now, it was four-terminal circuit. What I told you yesterday was two-terminal circuit. Usual theory of electricity, where we approximate the circuits with local resistors. There's voltage drop here, voltage drop here, current source here. These resistors will be the same in two-terminal and in four-terminal setup. But this is not the case of nanostructure. Yeah. One has to accept it. This is a property of a wave property of electrons, which can also put this way in such a way that there's a lack of equilibration. Fine, because yeah, if you would put it very far from the lead, where there are many channels coming to nanostructure, but all are reflected, then we will pick up voltage from all these many channels, and we will measure something different. Ultimately, we will measure this two-terminal connectors. All right. Did I say everything? Are there any questions about what I just said? All right, good. Let me go. Just go further. Let me check about quantum interference in very simple terms. There was a survey among physicists, very simple one, but it gave a question, an answer which I like. People were asked to select the most profound experiment in all history of physics. And that setup has won with a big score. This is double slit experiment. Right? Let me remind you, we have a source of waves at point A, electrons, light, whatever, doesn't matter, and we collect these waves at point B. Right? There are two ways for waves to go from B to A, which are distinguished by these slits. One, two. So let's figure out what would be probability to go from A to B, right? If you're kind of classical physicist, if you think about propagation of particles, you would immediately say, well, it's just a sum of probability to go through slit 1 and slit 2. This is not what I wouldn't even say quantum mechanics. This is not what wave mechanics tells us. In wave mechanics, the probability is proportional to the square of wave amplitude in B. And this amplitude is a sum of two amplitudes, A1, A2. So we need to square the sum. Okay, we get classical terms. But in addition, we have interference term, which for quantum waves is quantum. How to single out this term? Classical terms do not depend on the phase which is acquired by the wave when it moves from A to B. These terms do depend on the phase. They depend on phase shifts. So interference would allow us to see phase shifts. If we close one slit, there's no way to measure phase shift of this without just by measuring intensity, just measuring probabilities. All right, double slit experiment. Let's see how one can organize it in quantum transport. And let me just talk about phase shifts. A couple of interesting things to say about phase shifts. First of all, let me understand it for a wave which moves in some smooth potential. One-dimensional wave moving in a smooth potential, very similar to adiabatic transport, which we consider. Then, if I look at this phase in terms of phase vector, I understand that derivative of phase vector with respect to x is associated with a local wave vector. This wave vector depends on x because the particle is at the same energy E. But K is associated with kinetic energy, so it has different kinetic energy in different points. That's why this K is given by this formula. I just use that K squared by 2m plus potential energy should be the same. All right? Do you understand this? That's kind of correct formula, pretty formula, but it's not very intuitive. Let's do the following. Let us compute the energy dependence of this phase shift. So we assume that electron goes from x1, x2. This phase shift is accumulated between x1 and x2. So I just take this formula, differentiate it with respect to energy. What I find, differentiating this, that it is proportional to this velocity. I integrate it, and I get something pretty spectacular and constructive. Derivative of the phase shift with respect to energy is time. Is the time required to go from x1 to x2. Someone can get already some intuition about phase shifts, at least their energy derivatives are associated with what's the classical time of traversing a certain space. Voltage dependence. Again, I'm thinking of gate voltage, which influences electrons, changes chemical properties without really absorbing it. Right? So this gate voltage would just shift the energy. That's why its effect is proportional to this voltage times time. All right. Now we understand in pretty intuitive terms what are phase shifts which are due to potential energy, whatever complex it is. Right. So, point 1, point 2, the electron can go from 1 to 2 along a certain trajectory, one can go back. Let us understand that for our case, the phase shifts are precisely the same. Yeah, we just change the sign of the scale, but the direction is changed as well. So these phases are the same, and whatever they say the creator has made this world, and everything in it, including physics. But as to notations and terminology, which is commonly used in physics, it looks like the opponent of creator had something to do with this. This phase is called dynamical phase. And don't ask me why, just refer to the opponent. I don't know, but well, that's what everybody uses. Dynamical phase. Right. Complementary phase is acquired in magnetic field. How it does do so? We look at certain trajectory of the magnetic field. Again, electron goes from 1 to 2. Then the phase along this trajectory would be just momentum along this trajectory, integrated over small pieces of length L. We know that in what magnetic field does for charged particles, it modifies, elongates its momentum by this factor, by vector potential. So we see that vector potential, which is proportional to magnetic field, provides phase shifts. These phase shifts are opposite for two opposite directions. You go from 1 to 2, but you can already see that from the fact that they're proportional to magnetic field, which changes sign upon time reversal. Right? So this is alternative phase. Who knows, who has heard how this phase is called? Yeah? Yes?
Nazarov. Berry phase.
Oh. Precisely, yeah. Again, I don't know. I could theorize, but it's called phase. but it's completely ununderstandable for me why it's not geometric phase, why it's not orthogonal bone phase, whatever. But it is the term which everybody uses. This is geometric phase. Right, okay, we know now about phase shifts. Let me talk about orthogonal bone effect, which is after touching voltage leads, is second example that physical quantities are intrinsic for describing physical phenomena. Right? So how does it go? We still have double slit experiment, but next to double slit we put a coil which goes to this direction. Coil is there's current goes through the coil, and that creates magnetic flux inside the coil, and it doesn't create anything, no magnetic field outside. Now we want to check interference pattern here, and we understand that there are phase difference for electrons which follow path 1 and electrons which follow path 2, which goes through different slits. One should just believe in the formulas for geometric phase I've shown, and believe that a physical vector potential can do something. So there is no, again, there is no magnetic field, there are no forces acting on classical particle in this setup, but by magics of wave propagation, it is affected by our own phase. One compute this phase, it's just integral over the flux of a contour which rests this coil, and this is just full flux through the area. In terms of some quantity, which is called flux quantum, I would certainly put 2 pi here, but that's again another trick of notation. People have defined this quantity for superconducting particles for Cooper pairs which have charge 2e. That's why there is no factor of 2 here. All right. How to distinguish? Suppose there is this effect, and there is also some magnetic field leaking from the coil. How to distinguish it? Can easily distinguish by detecting periodic dependence of the signal upon flux. Right. Still, we are not in quantum transport. We kind of talking about freely flying electrons somewhere in double slits. Let us try to go to our business and understand interference in quantum transport steps. Again, using scatter matrix. And I hesitate to start with our own Bohm effect. Let's just look at double junction. Right. What is a star? We know pretty well how does it go in a single channel scatter. It's characterized by scatter matrix, the transmission coefficient. We put these two things in general. And it would be eventually very sensible task to determine the transmission coefficient of the setup in terms of transmission coefficients of the left and right scatter. there is a problem here, which rendering which those who are native Russian speakers have unfair advantage for. The reason is very silly riddle which Russian language speakers got in the age of 2, 3, so it remains for the whole life. The riddle goes as following. A and B have been sitting at the roof. A went down. B went down. What is there at the roof? Tell them. Come on. And, yes, and. We frequently try to forget for simplicity that if you talk about two objects in relation, that blue, which provides a relation, can also be important. The same here. It appears to be that the answer will depend on something which happens in between the scatterers and kind of glues them together. The answer will depend on the phase which is accumulated by an electron which travels from left to right scatter. That's the phase factor associated with this. You see, I'm looking at dynamical phase. All right, dynamical phase chi, and I want to know the answer. Let's see how to compute this. If I would be to write your first quantum book, I would certainly put it on the page number 12, because it's really, I would say, most important quantum mechanical effect, more important than scattering at rectangular barrier. But anyway, I got to you only at this stage, so please bear with me. What I have to go. First, I want to understand all elementary processes with which one can go from the left side to right side. What is the first one? Well, I traverse first scatterer, left scatterer. That happens with amplitude T. I accumulate phase shift, and I traverse right scatterer. That's most obvious contribution. But if one thinks about for a second, understands there's plenty of other contributions. These contributions differ by a number of bounces between the scatterers. So for instance, this one, traverse to the left, accumulation phase factor, or reflection from the right, again accumulation phase factor, reflection from the left, and then it goes through the right scatterer. Good, so what is the difference between these different ways? It's a factor like this. Now what we understand that we need to add amplitudes. We need to add amplitudes. We need to add all these amplitudes. This is geometric progression, geometric series. It's again the same, has the same relation to geometry as geometric phase has. All right. Anyway, geometric series, and we can sum it up easier. Right. How would I associate it with double slit experiment? Let me tell you that, and you would believe, that each trajectory which I draw is in fact a separate slit, a separate classical process, which can happen with a particle which goes through two barriers. Right? Quantum propagation is a result of interference through all these fields. Good. Let me just plot it. That's what I have. General expression, no sweat to derive it, and you see that this magical end between A and B really enters the formula. So this is the phase shift going here. Right, so we have I plotted versus chi. I could also plot it versus energy in some small interval, because as we heard, energy dependence of phase exists, and it just it is related to the time which particle spends traveling between two conductors. All right, that occurs like this. There's periodic modulation. If transmission is almost perfect, this modulation is small. You make the junction smaller, you expect the transmission is smaller, and it gets smaller, except the points when it doesn't get smaller. Let's see, other francophones or francophiles among the audience, parlez-vous français? Okay. What are two French names explaining this effect? Fabriquero. Right, so such effect first has been observed in optics when they push the light wave between two partial mirrors, and there were resonant transmissions at certain frequencies. That's what we see in electron transport. Right. Let me just tell rather instructive thing. If reflection coefficients are really small, we can visualize these levels as particles trapped between two barriers at certain energy. So there is a mechanism of making discrete energy levels in this scattering stuff. Okay, and there's some resonant transmission at these two levels. All right? Are you with me? Any questions? Who would like it? Who would like to have it at 15th page of your first quantum mechanical book? Still nobody. All right. Let's go further, and let me just become the pause. Yes?
What did you call quasi levels? What did you call quasi levels?
I call it quasi because it's not really levels. If I put a particle into this level, it won't be there forever. At any finite transmission coefficient, it will escape. But, okay, it's a small time of this escape, that's fine, I can think of quasi-levels. Right, how to do it correctly? How to solve these problems without just strict summing up all these trajectories. It's nice to visualize it, but for practical purposes, there will be too much trajectories. One just needs to solve for waves everywhere in the structure. So let's see, there's an incoming wave, reflected wave, wave amplitudes on both ends of this space between the connectors. and only one total wave. Now what we need to do first is to make equations for all these variables. How we can make equations? We can use scattering matrices. Left scattering matrices. There are important incoming particles, incoming waves with amplitude 1, amplitude B. They are transformed to outgoing waves, A, F total. The same for right matrix. And for spacer, the relations are very simple, just that phase factor is applied here and here. With that, yeah, that's how my students survive the exam. They make such equations and try to solve them. Good. Let us go to Aronoff bombing. Let us understand that one needs splitters to make Aronoff bomb ring in the paradigm I'm using. Why is it so? Because one should have some space to put magnetic flux. If I would just take two conductors in series, I couldn't put flux here. So I need to split channels to make the loop. Okay, so let us see. Setup, I put beam splitters. For instance, I could use reflections beam splitters. There are phases which should influence conductance of the setup. There are dynamical phases, chi's. There are Aronoff bomb phases, geometrical phases, phi's. Good. We understand the formulation of the problem. I would immediately switch to final formula, but you wouldn't understand it. Let's try to get it in a little bit more details. Let us talk about the language of trajectories. So now I write it for the loop. The simplest trajectories, which go from the left to the right, are those. One can go above the loop in upper arm, or one can go in lower arm. Right. I want to talk about more trajectories. It's not because I'm kind of too peculiar about this, or I love my stuff too much. Just bear with me, they really become important. But it's just all possible trajectories with one bounce. Yeah, for instance, this one, there is a transmission, it goes down, but it doesn't turn to here, it turns here, so it bounces and goes like this. All possible trajectories with one bounce. Good, let me understand that the total effect I could get if I look at pairs of different trajectories. So just take different pairs and see how they are manifested in interference. First of all, let me take two simplest trajectories, and this is precisely as in Aronoff bomb. However, if I count all phase shifts which are accumulated, I see that the probability of conductance depends not only on the flux which I put in, it also depends on the difference of dynamical phases. I just revealed that dynamical phase potential at this arm should not fit the potential of this arm. Good. So with this, the effect is periodic with a period of 2 phi naught. Let us average this effect over all possible dynamical phases. What will happen? It will vanish. If you average cosine of the phase, that will get to 0. It took some time for physicists to understand the following fact. If one looks in more complex trajectories and consider a pair of these, there is a possibility to cancel dynamical phase with a great precision. So, what is the difference between these trajectories? Eventually, they go through all arms, but they differ by circulation, by the way they go around the loop. This trajectory does it, let us see how the clock goes, clockwise, and this goes precisely the same but counterclockwise. Right, so we have two contribution depending on dynamic phase, and the one which does not. Right, let us see, that's the full solution. I wish I could have a simpler model, but that's how it goes. Even for a simple beam splitter I just used, it amounts to quite some equations. That's not very complex to solve it, but it's still some work. One cannot have a good answer. So I just plot it. And what I did, I plot here 3 traces versus flags. These traces, II and III, just taken at certain settings of dynamical phase. All right, one sees periodicity, and these traces are pretty different. What happens if I just consider plenties of these traces and sum them up if I will average over dynamical phase? Then I get this pink curve, and you see its periodicity is different. All right, signatures of interference in aronal bond setup. I would say pretty artificial. And now there's a final possibility for me to talk about experiments, about classic experiments. Okay, 80s. Perhaps your brain is told you that that was not really good time in general, even perhaps even worse than current time. There was a Cold War period, there was a competition between something which seemed to be very semantic. Right. That was an experiment of Soviet scientists, Arvin and Shalvin. So what they do, it was quite continuous setup. They use crystal whiskers, not from your mustache, but just there are some crystals, which I wonder what could they do with mustache whiskers. But anyway, they use crystal whisker insulator very thin one. And they evaporated some tin on the top of it. Thereby they formed a cylinder which was pretty small. I guess it was like 100 nanometers in this section. By technological limitations, they could make this cylinder short. So I believe it was about 1 millimeter. Good. And they put magnetic field like this, trying to get through cylinder. Tin could become superconducting. They work at temperatures to exclude superconductivity, so it's normal electron propagation was here. They plot resistance versus magnetic field. And you see there's some periodic signal. Right. There's also some ground linear background due to magnetic field. Also, in what looks attentively, it is just rather small resistance change, given the fact that the whole resistance, I guess, was about 100 ohm. Right. And my question to you is, it's given at the slide, but in pretty small font, so you have to pretend that you have not noticed. And tell me, explain me, which was the period of these oscillations, and why? It was crucial that this sample was pretty long, although circumference was small. Guess you also got the answer. That gas period of 5 months. So it corresponded to the spin oscillations to those I present in this slide. Why?
Diffusion trajectories. Diffuses trajectories.
It did not matter much whether these trajectories were diffusive. Even a diffusive trajectory would make it round, would pick up some iron components. It was important that these trajectories were many because of the volume of the sample. So all these trajectories would have different dynamical phase. The result should vanish. So they could only measure non-vanishing part. And okay, again, it's about terminology. If you want to be surprised, I can reveal that this is called weak localization. Fine. Shortly after that, the Americans wanted to show their superiority, and they made Aronov bomb experiment is a superior technology indeed. They just put a thin metallic film, evaporating it in the shape of the ring. Yeah. They look at the trace of resistance versus magnetic field. Again, it was pretty small signal, but measurable. And they, what they saw, they called grass. There were no regular oscillations. There seemed to be oscillations with many periods. What they did, they kind of made Fourier analysis. What this plot showed are most typical periods. They just make Fourier transform this curve and plot it versus magnetic field. So this is prominent peak which defines the period, and the period was 2 times I naught. What they managed to see is an effect which does not vanish upon averaging over dynamical phases. And again, the name does have to be explained. This is called universal conductance fluctuations. Good. Yes?
What is phi naught?
Phi naught is a flux quantum.
I would say, I mean, up to factor, is it superconductor?
There is only one flux quantum in this world, which is superconducting phase quantum. I'm sorry, my program has collapsed. Let's correspond to it. So, any questions I can answer without showing slides? Fine, I feel a bit tired anyhow.
Well, let's see, stand the speaker. In half an hour, the last lecture.